Okay, so I will speak about positive-unlabeled data and perhaps first some explanation what exactly it is. Okay, so let me first explain that it's not semi-supervised data, okay, as in the first talk. So we do not have access to a set of labels which are simply exactly true. Okay, so let me explain what happens here. So what happens is that here we have, instead, as in the classical case, when we consider classification problem, we have x and y's, and y's will be binary here. So here, instead of y's, we have a certain pseudo-label s, which belongs also to 0, 1, but it has a certain properties, and it reproduces y with a certain probability, okay? And the assumption is that simply we do have only part of positive labels, meaning that if the label is negative, real label is negative, so in this case s is equal to 0, so s will be my pseudo-label, and in the case when y is equal to 1, so s can be either 0 and 1, so that happens, okay? And there are many practical situations in which this can happen, and let me explain one perhaps not that very standard situation. We have citizen assembly example when simply randomly pick people, for example, for climate change citizens assembly, okay, which simply is a board which will advise government okay, on issues concerning climate change, and you pick those people randomly. Okay, and simply once somebody is picked, okay, chosen, or he or she can opt out or opt in. Okay, and of course, if he opts in, so it more or less it means that probably he believes in climate change. Okay, so let's y in this case would be equal to 1 when he is a climate change believer, and is equal to 0 and is climate change denialist. And if he opts 1. So opts in, so it means that he is climate change believer, but if he opts out, you do not know really, because it is arduous task. There are many meetings, and sometimes you simply do not have time to do that. So in this case, when you simply opt out, it means that either y is equal to 0, so you believe in climate change, or you simply you don't, okay? And you do not know simply what is the case. And of course, you have many examples which are more important. You have NLP, you have web pages tagging, and so on and so on. And let me explain in a picture what happens here. So we have here on the left, we have traditional supervised learning, and now imagine that all those blue triangles are covered, but also you have some positive data is also covered here. And of course, most interesting case is when those black boxes here depend on predictors. That's what happens, okay? And this is the case I will speak about, okay? So unobservable, and what is observable is simply posterior probability of S, of this pseudo-label I mentioned, okay? So now the issue is we have at our disposal only data concerning this, and we would like to have the knowledge about posterior probability of y and probability of E, probably. Okay, so it would be nice to have also some knowledge on propensity score. Okay, so let me explain the main issue here. The main issue here is that you have the following relation between what is observable and is not, that simply posterior probability of S is equal to product of posterior probability of y and posterior probability of propensity score, okay? And usually in the literature, people assume that propensity score is constant, but somehow it avoids the most important from the applicational point of view problem, namely when it's simply propensity score is not constant, okay? So now, how can you do this parametrically? This is where I will present you what will be here. What we have done with my team is simply some sort of humble parametric modeling, and I will explain why neural nets, at least in this approach, does not work that well here. So here we have, as I said, we have this product of posterior probability of Y and propensity score, and this is equal to posterior probability of S. And so if we have this model, so double logistic model, meaning that posterior probability and propensity score is modeled by logistic regression. So we have the result like that simply we can identify those guys, beta star and gamma star, up to a swap. And this, in fact, is true also in some generalized family when you impose some condition of so-called logarithmic derivative of the response function. So that's not only for this model, okay? And now, of course, when this result, you can try to use usual approach based on joint likelihood. So here you write down the likelihood for posterior probability of S, so it is written like that, and of course, okay, and you propose double logistic model, so you have this product on beta and gamma are your candidates for this model, and now you have this result, which is sort of simple, that if you take maximizer of your expected log likelihood, and simply to avoid this problem with the swap, you assume that the first norm of beta star is larger than the first norm of gamma star. So in this case, you can simply prove that maximizer of this guy is a true parameter. Okay, so this leads to joint method I'll speak about in a moment. Okay, so in fact, I can assert that maximizer of this guy is proved to be consistent, of the estimator of this guy is proved to consistent. Okay, so now the first proposal is simply to find estimators of posterior probability and this function E in sort of alternative ways. Okay, so let's see how this happens. So let's look at the posterior probability. So look at log likelihood for one observation, or cross entropy if you prefer this name. So of course we know that the expected value of the log likelihood will be, in this case, the true parameter. Okay, so now what we can do, because of course Y is not observable, we need to have a certain weight which in expected value will give the same value as the expected value of Y. And it is sort of simple because you have this weight which is given by simply indicated function of S equal to 1. So in the case when S is equal to 1, so your weight is equal to 1. And if S is equal to 0, so you have this probability which in fact turns out to be odds ratio of this propensity score and posterior probability of S. Okay, but now the question is whether we have solved our problem. And of course we haven't, because this guy depends on unknown posterior probability. So it means that we need to have the second equation for propensity score. And in fact it's quite easy to write this down, because in fact if we write the expected value, but now it is conditioned upon this strata equal to 1. So, and once again, we write log likelihood, but now for the propensity score. So this maximizer of this guy will be gamma star. Okay, so, but here the issue is that in fact we need to somehow to approximate the strata that Y, for those observations Y is equal to 1, and of course it is unknown. Okay, and that's in fact the main issue here. And let's look how this looks like. So here you have the empirical risk written down here for beta, and now we have the counterpart for propensity score. This is like this, but now the main issue here is that we have this P hat here, which simply corresponds to this strata. So we need to estimate this strata, and this in fact is pivotal problem here. I won't go into detail how it is done, but let's look at the algorithm. So here at the first step, we take the maximizer of the empirical risk likelihood for posterior, and we calculate the estimator of the posterior, and now we have the estimator for risk for propensity score, and we calculate the estimator of the propensity score, we calculate the estimator of the ratio, and we return to the first step. Okay, so now the main issue is how to estimate this strata, and we propose simply the estimation of the strata based on estimator of the previous estimator of posterior log likelihood. Okay, so now second proposal is just a joint method, which simply we take the joint empirical log likelihood and we maximize it over beta and gamma. Okay, and one theoretical result which perhaps is sort of useful, because usually people look at what is called regret of the estimator. So we take the maximizer, local maximizer over certain neighborhood of true parameter, and we can prove that in fact the difference between the true expected risk for my estimator and for a minimal value of this is bounded like that. So if you take a certain S, so S is in the denominator here, so we have the probability that you will exceed will be below such threshold with probability 1 minus S. So of course it is nice theoretical result, which simply shows you that in fact this estimator will be consistent in risk. Okay, so now let's speak about numerical part, and most results are contained in the paper. I will give the reference in a moment, but let's consider the scenarios. So the first scenario is very, very simple. So simply we consider a situation when the propensity score does not depend on x's, so it is just constant. And the third scenario, because second is just double logistic model. So here we have propensity score, which is simply geometric mean of univariate propensities, and univariate propensities are defined according to the value of the coordinate, which is simply linearly transformed to a certain interval p minus p plus. Okay, and just let's look at the perhaps first competitors. So state of the art competitors are so-called SAR-AM and labeled Bayes estimators, and also we include the oracle when simply Y is known, and naive estimator, which simply your estimator is based on your data, for which instead of Y's you have S here. Okay, so let's look at accuracy. Okay, so let perhaps to be more specific. So what we have done, we have taken certain data sets from UCI repository, and simply what we have done, we use this labeling scenario to artificially label some data. That's what according to those scenarios which are here, and here if you look at the results, so what happens here is we have some improvements. So we would prefer to look at the average rank. So the smallest rank the better. So for this two models method, we have the best result here, and there are some results for which the improvement is significant. If you look at credit A, so in fact it's better, and for vote is also much better. Okay, so standard errors are in 100, so they are negligible here. Okay, so if you look at, so also here you can, so the previous slide was for the accuracy. Here we have the results for approximation error when simply compare this oracle, and those results are more or less the same. Okay, so if you look at the picture, so the most important quantity here is C, and C is just probability of being labeled, overall probability of being labeled. So of course if C increases, so your accuracy increases. So the brown one method here is our proposal, and it is seen that in fact the main competitor here is this LBE method, which usually can get better for larger C, but the main advantage of this method we have proposed is for smaller C, that here you have some edge for smaller C, and also at some sets our method does not work this well, so here you have this LBE method much better than our proposal. Okay, so let me discuss at the end some issues which are here. So the first issue, and in fact the most important thing, is here: how do you estimate this set of positive observations? Of course, well, it is sort of understandable that once you can solve this problem, so it is sort of the whole problem will be solved because you are after those guys. Okay, this is the first thing. And the second thing is what is important, that this is sort of untackled till now. It is feature selection under arbitrary propensity score, or even under the situation when simply the propensity score is constant, because it's sort of very important. And the third thing is testing this selected completely at random assumption when simply propensity score is constant, meaning simply looking at the hypothesis that your gamma is equal to gamma 0, the intercept, and the vector will be equal to 0. And also, and I haven't sort of discussed this much, but we have this joint method which simply is based on joint log likelihood, which from the theoretical point of view is sort of nice. The problem is that for two models we have two criteria which are convex, but this guy, when you look at the log likelihood, is not convex, and that's the main problem. But still we believe, okay, till now we have used this algorithm, which simply tries to approximate maximizer of the empirical log likelihood. Does not work that well, but we still believe that in fact the underperformance of this joint method is based to, in fact, optimization issues, and we would like to somehow to have some additional work on this. And so let's look at the references, because they are sort of important. It's more or less the state of the art of the situation when you have this case when you do propensity score may not be constant. So it's SAR-EM method, which was the first method which was proposed here. And there's this LBE method, which I mentioned, and in fact those are two methods which are in the literature. There are two methods which are proposed in my group. It is two models, which is and joint, which I discussed, and there is other methods, in fact quite interesting method based on variational autoencoders and concatenated with some out of the distribution detection methods, which is in fact there are two papers on this which you can read. And in fact it is sort of nice method, and in fact it gives even better results than this method. But the issue here is that simply here you must know what is the probability of being in the class in the positive class. So you cannot avoid this. So in fact it's quite a good method, but you should have some additional knowledge of probability of y equal to 1. And it's also nice small paper when you simply reduce the number of parameters by using certain additional assumption on x's on your predictors, and in fact it is due to some properties of misspecified models, because you can look at this problem as a problem that you simply once you're applying logistic regression to your X, S, and S data, so you're misspecifying the model. Okay, so it is known that if you have some additional assumption on X's, so somehow you can still estimate your posterior probability consistently up to a constant. That's quite a nice result, and it was in fact used here. So I believe that's it. Thank you very much.